In this section, we're going to look at oscillations. An oscillation is a back and forth motion, just like the motion of a pendulum or the motion of an object attached to a spring. So this is a back and forth motion, a back and forth motion. A very popular type, very common type of oscillation is the periodic oscillation. That is an oscillation where a certain pattern repeats itself again and again. For example, if you have a pendulum, let go, the same pattern continues again and again. Such kind of an oscillation is called periodic oscillation. So let's define periodic oscillation. Periodic oscillation. This is an oscillation where a certain pattern repeats itself again and again. A certain pattern repeats itself again and again. And the time taken for one pattern is called the period. Time taken for one pattern is called period, and we're going to use capital T to represent it. Okay, and the number of patterns or number of cycles executed per second is called frequency. So number of patterns executed per second is called frequency, and we're going to use F to represent it. Frequency and period are inverse of each other, so you can say frequency equals 1 over period. Okay, and as you can see from here, the unit of frequency is 1 over second, which is called hertz, or represented by Hz. All right, but in this section, we're mainly interested in an oscillation called simple harmonic motion. A simple harmonic motion is a motion that varies like a sine or a cosine as a function of time. Okay, so an oscillation that varies like a sine or a cosine as a function of time, is called simple harmonic motion. It's called simple harmonic motion. If you plot the graph of a simple harmonic motion as a function of time, it might look something like this. It might look like a cosine or a sine. That's a function of time, and this is the displacement. So we're going to look at simple harmonic motion in some detail. So let's look at the kind of motion that we call a simple harmonic motion. Simple harmonic motion. This motion occurs when the force acting the particle is proportional and opposite to the displacement. This kind of motion occurs when the force acting on the particle is proportional and opposite to the displacement. That is, let's say if you use F for force, X for displacement with respect to the equilibrium position, displacement with respect to the equilibrium position to the, or relaxed, let's say equilibrium position. So harmonic motion occurs when the following condition is satisfied: is proportional to the negative of the displacement. Now, introducing constant proportionality, we can write this F equals negative Cx, okay, where C is a constant called a force constant, where C is a constant called force constant. Okay, obviously unit of C is Newton per meter. Unit of C is the unit of force, Newton, divided by unit of displacement, which is meter. Okay, now we're going to look at the dynamics of this motion. We're going to apply Newton's second law. Okay, Newton's second law implies that the force acting on the particle equals mass times acceleration. But if you remember, acceleration is the derivative of velocity with respect to time, or the second derivative of position with respect to time. Okay, so we have force equals mass times the second derivative of position with respect to time squared. Okay, so using this expression for force, we have the following equation: mass times the second derivative of position with respect to time is equal to negative C times x. Or we have mass times the second derivative of position with respect to time plus C times x equals 0. Okay, now let's try to make the coefficient of the second derivative 1 by dividing by mass. So we have the following equation: the second derivative of position with respect to time plus C over m times position equals 0 times m. Now we're going to say let C over mass equals omega naught. We're going to see later this is a kind of frequency, and it's called the natural angular frequency. We'll see later why it's called natural angular frequency, but for now let me say it's just natural angular frequency of the motion. All right, so I should put a square over here. So we have the following question: we have a second order differential equation which we can solve. Okay, plus omega naught squared times x equals 0. This is a second order differential equation, so that means its solution is two-dimensional. That is, if you can find two linearly independent solutions, then the general solution is the linear combination of those two independent solutions. Okay, so this is a second order homogeneous differential equation. Okay, so its solution is two-dimensional. Its solution is two-dimensional, which means if we can find two linear independent solutions, then the general combination is a linear combination of those two solutions. Which means if we can find two linearly independent, linear independent means not proportional, linear independent solutions, then the general solution is, then the general solution is the linear combination of these two solutions. The linear combination of those two solutions. Okay, now by direct substitution we can show that the functions sine omega naught t and cosine omega naught t are solutions. We can prove it by direct substitution. Okay, the functions cosine omega naught t and sine omega naught t satisfy this equation. And sine and cosine are linearly independent. Okay, that means the ratio is not a constant, which are linearly independent. That is, the ratio is not a constant, it's actually tangent. Okay, independent. So that means the general solution of this differential equation can be expressed as a linear combination of sine omega naught t and cosine of omega t. Okay, therefore the general solution can be expressed as follows: as x of t equals c1 cosine omega naught t plus c2 sine omega naught t. Okay, where c1 and c2 are arbitrary constants to be determined from initial conditions, where c1 and c2 are arbitrary constants to be determined from initial conditions, Okay, so we have the general solution in terms of two arbitrary constants. Okay, but now we're going to transform these two constants using we're going to transform these two constants into other more suitable constants. Now let's transform c1 and c2 to a and phi using the equations. The equation is c1 equals a times cosine phi and c2 equals a sine phi. Okay, we're just transforming the Cartesian constants to polar constants. Okay, so with that, the general solution can be written as, this implies x of t equals a cosine of phi times cosine omega naught t plus a sine phi sine omega naught t. Okay, now using the formula for the cosine of two angles, this would be equal to a times cosine omega naught t minus phi. Okay, so this is another way of writing the general solution. So instead of c1 and c2 as our arbitrary constants, we have a and phi as our arbitrary constants. Okay, so the a is the maximum value of the displacement. It's called amplitude. This is maximum value of the displacement. Okay, and it's called amplitude of the motion. Okay, now the constant c is called phase angle. This is called phase angle. its effect is to shift the graph to the right or to the left as it is. Its effect is to shift the graph to the right or to the left as it is. Okay, for example, you can say cosine is sine shifted by pi over 2. Okay, now the coefficient of time omega naught is called the natural angular frequency. Natural, we'll see later why we call natural angular frequency. It's largely because we don't have resistive force involved over here, such as air resistance, water resistance, and so on. So it's called natural angular frequency, and its effect is to determine how fast the particle oscillates back and forth. Determines how fast the particle oscillates back and forth. Oscillates back and forth. Back and forth. Okay. Now, if T naught is the period, that is the time taken for one cycle. If T naught is the period, then of course omega naught times T should be 2 pi, which is the period for cosine function. Okay, so if T naught is the period, then we have T naught times omega naught is 2 pi. Okay, so that gives us a relationship between the period and the natural angular frequency. So you've got 2 pi over T naught. Okay, so it's the relationship between the period and the natural angular frequency. And also, since period and frequency are inverse of each other, we can also write omega naught equals 2 pi times f naught. Okay, now if you remember, omega naught was equal to square root of c over m, that is the square root of the ratio between the force constant and the mass. So using this formula over here, omega naught equals 2 pi f naught, so we've got 2 pi f naught. This is a formula we started with. Remember, let me remind you over here. You see, we say let omega naught square equals c over m. This is the coefficient of x on this differential equation. Okay, that's where this formula comes from. So we have this equals square root of c over m. So another frequency is frequency equals 1 over 2 pi the square root of c over m. That's another formula we can use. Okay, and then since the period is the inverse of frequency, we also have T naught, which is 1 over f naught equals 2 pi the square root of m over c. Okay, so these are the expressions for the period, frequency, and angular frequency for this kind of motion. All right. Now let's look at velocity of this kind of motion. Okay, we know that velocity is the derivative of position with respect to time, right? So this would be the derivative of the amplitude times cosine of omega naught minus t minus phi. Okay, the derivative of this one is the derivative of cosine is negative sine, so you've got negative a omega naught and then times sine of omega naught c minus phi. So this is an expression for the velocity. Okay, acceleration, again you take the derivative of the velocity. Acceleration equals the derivative with respect to time. Okay, so if you take the derivative of this, the derivative sign is cosine, so we've got negative a omega naught squared. The derivative sign is cosine, negative sign, positive cosine, so we've got omega naught t minus phi. So this would be an expression for the acceleration. Okay, and for the force F equals m times a, right? So if you use this expression for a, we have negative a m omega naught, just m omega naught squared times cosine omega naught t minus c. Okay, but this one, m omega naught squared, equals the force constant, so you can say the force equals negative ca times cosine of omega naught t minus c. Okay, now let's see how we can determine the constants a and phi using initial conditions. Okay, so let's say determining the constants a and phi using initial conditions. Now suppose these are our initial conditions. The first is let's say the let the displacement t equals 0 is x naught, and let the velocity t equals 0 be v naught. Okay, so we have the following initial conditions, that is x at t equals 0 equals x naught, and then the speed at t equals 0 equals v naught. Okay, so as we've seen before, x as a function of time is a cosine of omega naught t minus phi. Okay, so this implies x at t equals 0 equals a. If we put 0 for here, we get a cosine of negative phi, but cosine is an even function, so it will be cosine of phi, and that equals x naught. And then the speed, the velocity, we show that there's negative a omega naught sine omega naught t minus phi. Okay, so the speed at t equals 0 is, if you put 0 over here, we get minus phi, but sine is an odd function, so it makes one positive, so you've got a omega naught sine phi. Okay, and that equals v naught. Okay, so our goal is using these two equations to express phi and a in terms of the initial conditions. Okay, so let's square these two equations. Okay, so we've got x naught squared equals a squared cosine squared phi, and then let's square this one over here. V naught squared equals a squared omega naught squared sine squared phi. Okay, now let me divide this equation by omega naught squared. Okay, so we can transform to x naught squared equals a squared cosine squared of phi, and this becomes v naught over omega naught squared equals a squared times sine squared phi. Okay, so if you add these two equations, you get the following. Adding, okay, you see from this side we get x naught squared plus v naught over omega naught squared, and the other side is a squared, and then you've got cosine squared phi plus sine squared phi. Okay, remember this equals 1. So you've got the formula a squared equals x naught squared plus v naught over omega naught squared, and then we take square root. The amplitude is square root of x naught squared plus v naught over omega naught squared. Okay, so if you know the displacement at equals 0 and the velocity at equals 0, you can calculate the amplitude of the motion using this equation. All right, now let's try to get an expression for the phase angle. We're using these two equations. These two equations over here. So let me write these two equations again. We have a omega naught sine phi equals v naught, and then the other equation is a cosine of phi equals x naught. Okay, now let me write this once again like this: a sine phi equals v naught over omega naught. Okay, dividing both sides by omega naught, and you've got a cosine phi equals x naught. Okay, now dividing this equation by this equation. Now a over a will go away. Sine phi over cosine of phi is tan phi. So you've got tan phi equals v naught over omega naught x naught. Okay, and that gives us phi equals tan inverse of the initial velocity divided by angle of vacancy and x naught. Okay, so using these equations, we can calculate the amplitude and the phase angle. So basically, let's summarize. If x at t equals 0 equals x naught, and v at t equals 0 equals v naught, we're saying then the amplitude equals the square root of x naught squared plus v naught over omega naught squared, and the phase angle equals tan inverse of the following expression: v naught over omega naught x naught, v naught over omega naught x naught. So if you know the initial conditions, we can use these formulas to calculate the amplitude and the phase angle. All right, now we're going to look at mechanical energy. Mechanical energy. Now it says, remember when the force is proportional to displacement, such as the force acting on an object attached to a spring, the force is conservative. We expect mechanical energy to be conservative. But let's proceed as follows. So what's mechanical energy? Mechanical energy is kinetic energy plus potential energy. This is kinetic energy plus potential energy. But as you remember, kinetic energy is always half times mass times speed squared. And the potential energy, we know the force, so we can obtain expression for the potential energy. The potential energy with respect to x equals 0, or the relaxed position, is the integral going from 0 to x, and then you've got negative c x prime dx prime over here. This is a force. This is the formula for potential energy. This is potential energy with respect to x equals 0. Potential energy with respect to x equals 0, or equilibrium position, you can say. Equilibrium position. Okay, so what does this integral gives us? You've got half c x squared. So this is a form of the potential energy for this kind of motion. Okay, so we have an expression for the mechanical energy. So the mechanical energy for this kind of force is half m speed squared plus half the force constant and then displacement squared. Okay, this is the form of mechanical energy for this kind of motion. Okay, now we know that x equals a cosine of omega naught t minus phi, and v equals the derivative of this expression, which is negative a omega naught times sine omega naught t minus phi. Okay, so this, we have mechanical energy equals half times mass times speed, which is this one, negative omega naught sine omega naught t minus phi squared, plus half c, which is x squared, which is this one, the displacement a, cosine of omega naught t minus phi squared. Okay, now let's simplify these expressions. If you take this out of this bracket, we get half mass, and then we have a squared omega naught squared, a squared omega naught squared, and then you've got sine squared of omega naught t minus phi. Okay, and for the second one we have half c, you've got a squared, and then we have cosine squared omega naught t minus phi. Okay, now remember m times omega naught squared equals c. Okay, but m omega naught squared equals c, so instead of m omega naught squared we can put c, so this equals half c a squared sine squared omega naught t minus phi plus half c a squared cosine squared omega naught t minus phi. Okay, so when we add this, we just get this one, half c a squared. So you see, the mechanical energy is actually independent of time, it's a constant. Okay, so this implies mechanical energy is equal to half c a squared. Okay, that is, mechanical energy of harmonic motion is a constant independent of time. Mechanical energy of a harmonic motion is constant, that's independent of time, of course, as expected, because the F equals negative Cx is a conservative force as expected. So mechanical energy is a constant, is given by this expression for an object undergoing a harmonic motion. All right. So now we're going to look at examples of harmonic motion. Examples of simple harmonic motion. First, we're going to look at the motion of an object attached to a spring. Motion of an object attached to a spring. Okay. Now the motion of an object attached to a spring is characterized by Hooke's law. We have already stated Hooke's law, but let me state it again. Hooke's law states that the force due to a spring, is proportional and opposite to the displacement. Which is basically the definition of a simple harmonic motion. That's why an object attached to a spring will undergo a simple harmonic motion. So let's say this is the relaxed position of the spring. This x equals 0. Okay. So when you extend it, this would be our displacement x, and the spring would be pulling back. Okay. That's why they're opposite in direction and proportional. And if you double the extension, the force will double, and so on. And if you compress it like this, then this would be the compression or displacement, and the spring would be pushing the opposite direction. Okay, so mathematically this is written as Fs equals negative kx, where k is a constant called Hooke's constant, where k is a constant called Hooke's constant. Okay, so basically this equation is identical to the equation of a simple harmonic motion. Okay, comparing with the simple harmonic motion force equation, we have F equals negative Cx, implies that the motion for an object attached to a spring should be simple harmonic. This implies that the motion of an object attached to a spring should be simple harmonic, and all the equations we derived so far for simple harmonic motion apply to a spring. Okay, that means all the formulas for simple harmonic motion apply with C equals K. Okay, so some of them were, we have omega naught equals square root of, instead of C we're going to use K, so we've got M over here, and then the frequency was 1 over 2 pi square root of C over M. Now we have K over M, which is constant divided by M, and the period would be 2 pi square root of M over K. So all the formula for simple harmonic apply, and also we have the formula mechanical energy equals half Ca squared, is going to be half Ka squared. This is the mechanical energy of a simple harmonic motion. All right, so all the formulas would apply for a spring, because the motion of an object attached to a spring is simple harmonic. All right, now let's look at an example. Let's say a spring extend this by, let's say, 1 centimeter when an object of mass 1 kilograms hangs from it. Okay. All right. Now let's say it is extended maybe by 2 centimeters and let free to oscillate. Okay, so let's answer some questions. A, what is its Hooke's constant? What is its Hooke's constant? Okay, so we're told that let's say this is the relaxed position spring. When an object of mass 1 kilogram hangs from it, it extends by 1 centimeter. All right, so the force pulling down is mass times gravity, mg. Okay, and since this object is equilibrium, then of course the force the spring also would be mg. Okay, so you've got Fs equals mass times gravity, that's 1 kilogram. This is gravity about 10, that's 10 newtons, and that causes an extension of 1 centimeters, that's x. Okay, that's 0.01 meters. All right, so we can calculate k. If you're not interested about sign, it will be Fs divided by x, so that will be 10 newtons divided by 0.01. Okay, so the Hooke's constant for the spring is 1000 Newton per 1000 newtons per meter. All right, now B, should we modify this? It's extended by, this is with an object of mass 2 kilograms attached to it. Okay, attached to it. So we have the following. We've got the spring over here. This is 2 kilogram mass attached to it. Okay, so the question is calculate the time taken for one cycle. The time taken for one cycle. Okay, all right, so we're looking for the period. Period is 2 pi square root of m over k. Okay, so our mass is 2 kilograms, and our k is 1000. Okay, so the period would be, period is 1 over 2 pi square root of, the mass is 2, and then we get 1000 that's 1 over 2 pi square root of 1 over 500. Okay, so this is approximately 100, will be 1 over 10, 2 point something. I would say approximately 2 point, this will be 1 over 2.5, and then this is 1 over 10 times 2.25, or about 20.5. All right, so this would be the period of the motion. That's how long it will take to make one complete revolution. All right, now C, give a formula for the displacement as a function of time. Okay, all right, so we're looking for x of t question mark, but we know that this is a times cosine of omega naught t minus phi. Okay, so omega naught is square root of k over m. Okay, that is square root of k is 1000 and then minus 2, so that is square root of 500, which is about approximately about 22.5. okay, that is Newton per meter. Okay, all right, but we have to determine a and phi, so we're going to use initial conditions. Okay, so it's extended by, look, by 2 centimeters. It's extended by 2 centimeters and then let oscillate. So its displacement at t equals 0 is 2 centimeters. So from that we see that x at t equals 0, which is our x naught, is 2 centimeters or 0.02 meters. And of course, when I let it go, it starts from rest. So v at t equals 0, which is v naught, equals 0. Okay, so using these conditions, we can determine the values of the amplitude and phi. Okay, so we're going to go back to these formulas over here. Okay, A equals square root of x naught squared plus v naught over omega naught squared. Okay, so this is square root of, this is 0.02 squared, and then v naught is 0, so this will be 0. Okay, so the amplitude is simply 0.02 meters. Okay, and now let's look at the phase angle phi. We see that phi equals tan inverse of v naught over omega naught x naught, right? So over here, but v naught equals 0, so this should be equal 0 because v naught is 0. Okay, so the phase angle is 0. So this is a formula: x of t equals a cosine omega naught t minus phi. We plug in everything, we get x of t equals the amplitude 0.02, and we get cosine, this is about 22.5 t, and the phase shift is 0. This is 0. So basically the formula is 0.02 cosine of 22.5 t. All right. Okay, let's add one more question. Let's see. D. Calculate its velocity by the time it is extended by 1 centimeters. All right. So we can use the formula for mechanical energy. Remember, we've got mechanical energy equals half k a squared, but we know that this also equals half m v squared plus half k x squared, right? So the question is, calculate v, this v over here, when x equals 1 centimeter. Okay, so let's move this around. We've got half m v squared equals half k a squared minus half k x squared. We can factor out the half k. We've got half k, and then we've got a squared minus x squared, right? That is half mv squared. Okay, and then the factor of half goes away, and now let's divide by m. So we've got v squared equals k over m, and then you've got a squared minus x squared. Okay, that is v equals plus or minus, now remember, this is omega naught squared. yeah, k/m equals omega naught squared. So you've got omega naught squared and then square root of a squared minus x equals 0. Okay. So the question is, calculate v when x equals 1 centimeter. Okay. When x equals 0.01 meters, and remember, a is amplitude, 0.02 meters, and omega naught we just calculated to be about 22.5, or this omega naught squared equals 500. Okay, so you've got the speed when x equals 0.01 is plus or minus 500 square root of 0.02 squared minus 0.01 squared. Okay, so we can factor out this is 2 times 10 to the power -2, so we can divide by 10, and then we got square root of 2 squared minus 1 squared, which is 3. So this is plus or minus 50 times square root of 3 meters per second.